Good day. We are here today to talk about section 4.3, which is the last of 3 sections in chapter 4, talking about bivariate distributions of discrete random variables. If we let x and y be discrete random variables, we have seen that we can talk about the probability that x takes on a specific value little x and y takes on a particular value little y. This we call our probability mass function, our joint probability mass function, little f of x, y. So that's our joint probability mass function. Next, we looked at the marginal distribution, f sub x little x, which tells us the probability that our random variable x takes on a specific value little x. This is our conditional distribution of x. Our conditional probability mass function of x. And really what it does is it tells us if we weren't thinking about y at all, what would be the value that x would take on each of the values in its support. We talked about marginal distribution can also be found for y, little f sub y of y. That tells us the probability that y takes on a particular value. This time if we're not thinking about x at all. This is another conditional probability mass function. And this week what we're going to focus on is conditional distributions. So given that we know the value of one of the variables, what's the probability that the other variable will take on a particular value? So the notation that we use g of x given y, which is going to tell us the probability that x takes on a particular value little x, given that we know that the variable y takes on a particular value little y. Sorry, these are not conditional. What was I thinking? These are marginal distributions. I saw that word conditional up there and I just copied it down. If we're thinking only about x, it's marginal. If we're thinking only about y, it's the marginal of y. When we're thinking about x given a particular value of y, that's our conditional distribution. This is our conditional probability mass function of x given y. And h of y given x tells us the probability that y takes on a particular value little y, given that x takes on the value little x. And we call that the conditional probability mass function of y given x. And these two distributions are what we're going to focus on primarily today. Although we'll need these other pieces along the way to get there. So we're going to have a little review of all of the stuff that we've done so far in chapter 4. Now remember when we talk about conditional probability, we said that the probability of A given B was the probability of A intersect B divided by the probability of B. We had 2 events A and B. Suppose we consider event A is that x takes on a particular value little x, and event B is that y takes on a particular value little y. Then the probability of A given B, which is the probability that x takes on a particular value little x, given that y takes on the particular value little y, is going to be the probability of x equals little x and y equals little y, divided by the probability that y is equal to little y. And we know that this is our joint PMF divided by our marginal probability mass function of y. So when we look at the formula that we see, that's given in the book. This really is the same conditional probability that we've been looking at since back in chapter 1. It's just expressed in terms of these probability mass functions, the joint probability mass function divided by the marginal probability mass function. But it's exactly the same idea of conditional probability that we've always been working with. Similarly, if we're interested in the conditional distribution of y given x, and our book chooses to use G for the conditional of x given y and H for the conditional of y given x, we just reverse the roles of x and y. We take our joint divided by the marginal distribution of x. And that would be our conditional distribution. Once we have a couple things to note, if we look at these values, if we look for sort of look at the conditional distribution of x given a particular value of y, if we look at sort of summing them for all the values of x, it needs to add up to 1 because it's going to give us a probability mass function. If we have a probability mass function, it has to sum to 1. And the same would be true for the conditional distribution of y given x. Okay. The next thing I want to mention is just finding the mean and variance of a conditional distribution. The expected value of x given that y equals some particular value. What we're going to use is we're going to need to find that expected value. We'd first start by finding trying to remember, g of x given y for all x that are in the support of the random variable x. And then we would simply find the mean of x given y by adding over all the values in the support of x times this conditional probability that x equals x if y is y. I'm going to do an example, but just to kind of walk through how to do that. If we wanted to find the expected value of x squared, given that y is equal to particular value little y, again, we'd sum over all the values in the support of x. Instead of taking just x, we'd take x squared times that conditional probability, add them up, and then we could find the variance of x given y by taking the expected value of our x squared given y minus our mu of x given y squared. And I'll go through an example that will go through and actually do this, but I just wanted to kind of mention the process first. So you need to start by finding the conditional distribution, and then you use it just like you'd use any other probability mass function to find the mean and the variance of that distribution. Okay, so what I'm going to do is do a really big example, and we will take a look. Going through all these steps and also see the relationship between the conditional distribution and the squares line and a couple of other little pieces of sort of drawing our attention to a couple of other important things along the way. So the example that we're going to do is going to be looking at rolling a fair four-sided die twice. So the outcome space in terms of the things that, we could have the die land with a 1 and a 1, a 1 and a 2, and so on. We've got 16 outcomes in the outcome space. X is the number of even numbers that land facing up, and Y is going to be the number that lands facing up on the second roll. And we are going to look at the probability mass function, joint probability mass function for X and Y to start with. Then we'll look at the marginal distributions, conditional distributions, and finding expected values. Okay, so let's see. First I'm going to start by looking at the joint probability mass function. So this is going to give us our little f of X and Y. So let's see. Y is the number that lands up on the second roll, so this is going to take on values between, so it could be 1, 2, 3, or 4. There's our Y. And X is the number of even numbers rolled, so we might roll no even numbers, 1 even number, or 2 even numbers. Now, it's possible if we roll no even numbers, then we definitely aren't going to roll a 2 or a 4 on the second die. So it'll have to be a 3 or a 1. And there are 2 out of the 16 outcomes that are going to result in each of these. So we've got 1/8 probability associated with both of those outcomes. If we have 1 even number rolled out of the 2 dice, it could happen on the first or second one. So it's possible that we could roll any of these values on the second die. And each of these also, if we go through our outcome space and look, we'll find has a probability of 1/8. If we roll 2 even numbers, then we know we're definitely going to have either a 2 or a 4 on that second die, because we couldn't have any odd numbers rolled at all. And again, the chance of each of these outcomes is 1/8. And if you need to kind of spend more time working through that, this is a long example. I want to make sure I have time to finish it. So you can always look through the outcome space and look at it, think about what X and Y would be for each of those, and just kind of verify those probabilities for yourself. Okay, so a couple of things to note here. One is that because we have a support that is not rectangular, these are not independent random variables. They are dependent on each other. If I know that I had 2 even numbers, then I couldn't have rolled a 1 on the second die. So there is dependence here. So just a note, X and Y are dependent. Okay, so we're going to take a look next at the marginal distributions. So I'll look at the marginal distribution for X. I'll tabulate it. Notation for the marginal is little f sub x of x. I'm going to list all the elements in my support of x, which are 0, 1, and 2. To find the probability associated with them, remember I'm going to add, for x, I'm going to add the values that are included here. So I've got 1/8 plus 1/8 gives me 1/4 chance that x is equal to 0. I've got 1, 2, 3, 4/8, which is 1/2 chance that x is equal to 1, and 1 2/8, 1/4 chance that x is equal to 2. I can also find the mean and the variance of this marginal distribution. The mean of x, which is just the expected value of x. I can add, for all the values x that are in the support of x, x times our marginal distribution, marginal distribution. So I'd have 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4 gives me a mean of 1. I can find the variance, sigma squared sub x. It's going to be the expected value of x squared minus our mean of x squared. To find the expected value of x squared, remember I can sum, for all the x that are in the support of x, x squared times that marginal probability that x is equal to x. If I do this, I'm going to get 0 squared times 1/4 plus 1 squared times 1/2 plus 2 squared times 1/4, which gives me the expected value of x squared equal to 1.5, which means that my variance of x is the expected value of x squared, 1.5, minus the mean of x, which is 1, squared, which gives me a variance of 0.5. I can go through the entirely same process to find the marginal distribution of y. The marginal distribution of y. I can tabulate it. I know y can take on the values 1, 2, 3, and 4. That's the support for y. So I need to list all those values. And then to find the marginal probability that y takes on each of these values, say, okay, there's 1 2/8 at 1, so that's 1/4. 1 2/8 at 2, again 1/4. 1 2/8 at 3, 1/4. 1 2/8 at 4, 1/4. I could also go through the same process I did over here to find the mean of y, which is the expected value of y, is equal to 2.5. I'm not going to do all the calculations. I think we get the idea. And that the variance, sigma squared of y, is equal to 1.25. So there are marginal distributions and the marginal means and variances. Now, one thing I'd like to point out is that if we look at the point x equal to 1 and y equal to 2, and we look at the joint probability that x is equal to 1 and y is equal to 2, 1, 2, that's 1/8. If we look at the marginal distribution for x, we can see that the probability that x takes on the value 1 is 1/2. The probability that y takes on the value 2 we can get from the marginal distribution, that's 1/4. And we can see that the product of these marginal probabilities is equal to the joint probability, right? This is just an example to show you when we talk about independence, we say to be independent, f of x times y must equal the marginal for x times the marginal for y. I just wanted to point out that this needs to be true for all xy pairs. In our support in order to have independence. This is a situation where we have dependent variables, and yet this equality is satisfied for this particular xy pair where x is equal to 1 and y equals 2. So I just want to reiterate that in order to be independent, we don't need to show that the joint distribution is the product of the marginals for just one point. We need to show that it's true for all points. If it's violated at any of the points, then it is not independent, it's dependent. So in this case, f of 1, 2 is equal to f sub x of 1 times f sub y of 2, even though x and y are dependent. Okay, so we've got our marginal distributions. We've got our joint distribution. So now on to look at our conditional distributions. Oh, no, I'm going to do one other thing first. Sorry, I forgot I was going to do this, just to get us all the way through. I'm also going to look at the covariance of x and y before we go back to that. So the covariance of x and y is the expected value of x times y minus the mean of x times the mean of y. We want to calculate it. The expected value of x times y we can find by taking the sum for all of the xy pairs in our support of x and y. We take x times y times that joint distribution, gives us the probability that x equals x and y equals y. So in this case, looking at our joint PMF, we'd say, okay, let's see. We've got the x, y pairs with 0 in them. So we've got 0 times 1 times 1/8 plus 0 times 3 times 1/8 would have x equals 1 and y equals 1. 1 times 1 times 1/8 plus x equals 1 and y equals 2. 1 times 2 times 1/8 plus 1/3. 1 times 3 times 1/8 plus 1 and 4. 1 times 4 times 1/8 plus, when x is equal to 2, we can have y equal to 2 times 2 times 1/8 plus 2 and 4. 2 times 4 times 1/8, which gives us an expected value of x times y equal to 2.75. So if I want to find the covariance of x and y, I have 2.75 minus my mean of x, which was 1, times my mean of y, which is 2.5, and this gives me a covariance of 0.25. From there, we can find the correlation by taking the covariance of x times and y, dividing it by the standard deviation of x times the standard deviation of y. Our covariance we just found is 0.25. Our standard deviation of x, we know the variance is 0.5, so the standard deviation is going to be the square root of 0.5. The standard deviation of y is going to be the square root of the variance of y, so the square root of 1.25. And that's going to be our correlation between x and y. Can also look at the least squares line. equal to the mean of y plus correlation times the standard deviation of y divided by the standard deviation of x multiplied by x minus the mean of, sorry, this should be the mean of y, mean of x, sorry. Okay, so we've got our least squares line. We know the mean of y, we found earlier, was 2.5, plus our correlation is 0.25 divided by the square root of 0.5 times the square root of 1.25. Our standard deviation of y is the square root of 1.25. Standard deviation of x is the square root of 0.5. Multiply that by x minus the mean of x. The mean of x was 1. If we simplify, this gives us 2.5 plus 1/2 x minus 1. So our equation for our least squares line is 2 plus 1/2 x. So I'm just going to sketch that onto our plot. So it's going to cross the axis here at 2, and it is going to increase by half each time, so it's going to come through here and then up here. So here's our least squares line right here. Whoops, kind of missed there, but here's our least squares line. Okay, now I'm ready to go to conditional distributions. All right, so conditional distributions. Conditional distribution, let me just make sure I'm on the screen here. Okay, so first we'll look at the conditional distribution of x given y, which uses the notation g of x given y. We find this by taking our joint, f of xy, divided by our marginal distribution, f sub y of y. So for instance, I'm going to, for y equals 1, I'm going to find g of x given y equals 1. So if I know that I roll 1 on the second die, what's the probability that I roll 0, 1, or 2 even numbers in the 2 die? This is what we're going to look at. So I can tabulate this. I can look at my values of y. I know looking, sorry, I'm looking at tabulating for x, conditioning on y. So I know that x can take on the values 0, 1, or 2. That's the support of x. I'm going to find for each of those values the chance, probability that x takes on each of those values given that y is equal to 1. Now to find this, I'm going to take my joint probability. So let's see, the probability that x is equal to 0 and y equals 1, 0, 1, that's 1/8. I'm going to divide it by the chance that y is equal to 1. The chance that y is equal to 1 is going to come from my marginal for y. It's 1/4. So I divide 1/8 by 1/4, and I get 1/2. For 1, 1, my joint probability mass function gives me 1/8. I divide again by my marginal probability that y is equal to 1. We said that's 1/4. That gives me 1/2. For 2, 1, my joint probability mass function at 2, 1, it's not part of the support, so probability is 0 that have that. Divide again by our marginal probability that y is equal to 1, gives me 0. So you can see that if I know that y takes on the value 1, then there's a 1/2 chance that x is equal to 0 and a 1/2 chance that x is equal to 1. And if I look at my distribution, this makes total sense. I say, okay, there's equal probability of each of those two outcomes. Those are the only two possible outcomes if y is equal to 1. So it makes sense that, you know, the chance of each one of those happening, if I know that y is equal to 1, must be 50%. Now, if I want to find the expected value of x, given that y is equal to 1, I'm going to add up for all of the values in the support of x. I'm going to take x times my conditional probability that x takes on that value given that y is equal to 1. So I come over and I say, okay, I've got x is equal to 0, and the conditional probability of that, if y is equal to 1, is 1/2, plus x might be equal to 1. And if I know that y is equal to 1, the chance of that being the case is 1/2. I've got x of 2, but if y is equal to 1, the chance of that happening is 0. And so my expected value of x, given that y is equal to 1, is 1/2. And again, this makes sense if we look at it. We're looking only here. We've got two outcomes at 0 and 1 that are equally likely, so it makes sense that the expected value would be halfway in between. Right? Just sort of instinctively, it's a sensible value. To find the variance of x given that y is equal to 1, I'm first going to find the expected value of x squared given that y is equal to 1, and then I'm going to subtract off, and this, we can use the notation here, the mean of x given y is equal to 1, and I'm going to subtract off that mean squared. So to find the expected value of x squared, I'm going to take my x squared, so 0 squared times 1/2 plus 1 squared times 1/2 plus 2 squared times 0. Then that's going to give my expected value of x squared given y equals 1. And then I'm going to subtract off the mean squared, 1/2 squared. And I can find that the variance is going to be equal to, let's see, I've got 1/2 minus 1/4 is going to be 1/4, or 0.25. Okay, so just looking at how we can find mean and variance for a conditional distribution. We can also look at conditional distributions. We could also similarly do the same kind of thing for all of the other possible values of y. We could find g of x given that y is equal to 2, g of x given that y is equal to 3, and the conditional distribution of x given that y is equal to 4. I'm not going to go through all of those, but same kind of process. Next thing we're going to take a look at is the conditional distribution of y given x. So h of y given x is our conditional distribution. Y given x. again, we'll need to work with our joint probability mass functions and our marginal probability mass functions to find them, because this conditional probability that y takes on the value little y, given that x is equal to x, is equal to the joint probability that x is equal to x and y is equal to y, divided by the marginal probability that x is equal to little x. Just scooch my page so I don't have to go through all of the calculations slowly. Okay, so let's look at, for the situation when x is equal to 0. We know that y, the number that comes up on the second roll, can take on the values 1, 2, 3, and 4. That's our support of y, so we're going to list them all. And we're going to find the probability that y takes on each of those values, given that x is equal to 0, and that's our h of y, given that x is equal to 0. And to find this, we're going to find our joint divided by our marginal. So let's see, we've got our joint probability that x is 0 and y is 1. 0, 1, there's a 1/8 probability of that, divided by the probability that x is equal to 0. The probability that x is equal to 0 we get from our marginal is 1/4. So this is equal to 1/2. For 0 and 2, you can see we've got a joint is at 0, divided by 1/4 gives us 0. 0, 3, we have 1/8 divided by the marginal probability that x is equal to 0, which is 1/4, gives us 1/2. And for 0, 4, there's no probability of that event occurring. So our joint distribution, our conditional distribution of y, given that x is equal to 0, is given here. Notice that this is a probability mass function, so that the probabilities have to sum to 1. 1/2 plus 1/2 equals 1. And then again, I can find the mean of x, given that, mean of y, given that x is equal to 0. I'm going to sum over all the y that are in the support of y, our y times that conditional probability that y takes on that value given that x equals 0. It's going to give me 1 times 1/2 plus 0 plus 3 times 1/2 plus 0 gives me 2. If I go through the same kind of process, I can, for x equals 1, I can find the conditional distribution that y takes on the values 1, 2, 3, and 4. I'm not going to go through all the details like I did on the first one doing the calculations. You can check them yourself. But we get a distribution that's 1/4, 1/4, 1/4, 1/4, and the mean of this conditional distribution of y, given that x is equal to 1, is equal to 2.5. And finally, we could do the conditional distribution for x equals 2. Y again can take on the values 1, 2, 3, and 4. We're going to find the conditional probability that y takes on each of those values, given that x is equal to 2. And this time, we get a conditional probability mass function as given here. And an expected value of y, given that x is equal to 2, that is equal to 3. So I just want to show, going back to our joint PMF. If I look here, this is my expected value of y, given that x is equal to 0, is 2. The expected value of y, given that x is equal to 1, is 2.5. And here, the expected value of y, given that x equals 2, is equal to 3. And I'm just kind of pointing out that these expected values fall perfectly on our least squares line. So when we have a linear relationship between x and the expected value of x, y given x, then they will fall perfectly on the least squares line. Want to mention also, though, that this won't always be true. If it turns out that there's not a linear relationship between the expected value of y given x and x, we won't have them fall on the least squares line. And I have an example to show you. So here's a probability mass function graphed, and this is the least squares line. Now, if we were to find the expected value of y, we've got our x and our y. If we were to find the expected value of y, given that x is equal to 1, it's going to be 1.5. You can see that makes sense. It's halfway between the 1 and the 2. They have equal weight. I'm not going to go through all the calculations to show it because it would be very time-consuming to do them all, just to kind of give us a sense. If we know that x is equal to 2, if we were to find the expected value of y, given that x is equal to 2, it would be up here at 2.5. And if we were to find the expected value of y, given that x is equal to 3, you can see in this case those expected values don't have a linear relationship between x and the expected value of y given x, and so they don't fall on the least squares line. So if there's a linear relationship in the means, then it will fall exactly on the least squares line. If there's not a linear relationship in the means, it won't fall exactly on the least squares line. This is there's not a lot of sort of connection, like why does this matter, made in our textbook, because our textbook is, although we call the course applied probability, isn't particularly applied in terms of doing data analysis. But the reason that this idea is relevant is just to remind us that if you are working in a situation where you are fitting a linear model to data, if you have a linear relationship in your data, then fitting a least squares line to the data will give us a useful way to try to predict the mean of our y variable given a value of x. However, if we have a situation where we don't have a linear relationship in the data, and that's sort of what this is illustrating, then the least squares line is not going to be particularly useful in trying to predict the expected value of y on the basis of x. So I don't think that connection's really sort of brought out in the textbook, but that's really sort of the reason I think that they talk about this, even though they don't explicitly make the connection. So that is the end of my extremely long example. I know that there is a lot there. I hope that if you have any questions about it, or if you, as you're working through some of the steps that I didn't do completely out, if you come across some questions, feel free to ask. I'm happy to answer questions. But I hope it was helpful and will guide you as you try to sort of synthesize all the material in those first 3 sections so that we can have a good performance on the quiz this week. All right, have a good day.